Bismillahirrahmanirrahim. I am Mazhar Javed, Faculty of Electrical Engineering, Ghulam Ishaqa Institute of Engineering Sciences and Technology. You are welcome here in Linear Control System EE-341. This lecture starts with the discussion of CLOs related to this topic, and then we review the few terms and also review the RH criterion and how to develop the Routh table. And there are two special cases for the Routh-Hurwitz. First one is when the first term in the column is 0, how to handle this situation and what type of result will be. And the second special case is when the whole row is 0. And also we apply the RH criteria in state space, and also we will see that how to RH criteria is helpful to design a proportional or controller. And let's see. This lecture is based on the CLO2, which is the analysis part, and it will be helpful to design the controller, which are the parts of CLO3 and CLO4. Total response of LTI system is given by, which consists of force response and natural response. If we find the value of the natural response at time equal to infinite, if this response approaches to minimum values, approaches to 0, then we can say system is stable. If these responses are growing, then we can say system is unstable. In between the stable and unstable, if the response is not varying or oscillating, then we can say system is marginally stable. For bounded input, if the output is bounded, then we can say system is stable, and if for the bounded input output is unbounded, then we can say system is unstable. If we want to find the stability criteria by using the location of the poles in a complex plane or in S-plane, if the poles are lies on the right half plane, then we can say system is unstable. If the poles lies on the left half plane, then system is stable. This is the complete picture of the stability by using the S-plane or the complex plane. System is stable if the poles lies on the left half plane, and system is unstable if the poles lies on the right half plane. If the poles lies on the vertical axis or the imaginary axis, then behavior is marginally stable or the oscillatory behavior. If the poles are lies on the real axis, then only exponential behavior is showing. If the poles are lies on the right half plane, then growing exponential, and if the poles are lies on the left half plane, then behavior is decaying exponential. If the poles deviate from the real axis, then behavior is sinusoid. On the left half side, decaying sinusoids, and on the right half plane it is a growing sinusoids. And if the pose lies on the imaginary axis or on the vertical axis, then behavior of the system is pure sinusoids. If the closed loop transfer function is given, for example, this is the closed loop transfer function of negative feedback system, then by using this characteristic equation, we can find the location of the poles by using the RH criteria. Before going to apply the RH criteria, we have to check some RH necessary conditions. Okay, a closed loop transfer function is given where P of S representing the closed loop zeros of the systems and Q of S representing the closed loop poles of the systems. And from the characteristic equation, are simply Q of S is representing by this equation. So conditions are simply, we can say, if the all the coefficients of the Q of S polynomial are present, then we have to apply the RH criteria. If any coefficient is missing, then systems is already unstable. Similarly, if all the signs of the polynomial is positive or negative, then we have to apply the RH criteria. In other way, if the both signs are present in the characteristic equation, then system is already unstable. After checking the necessary conditions of RH criteria, after applying the RH criteria and developing a Routh table, in a complete table, if the first column have the same sign, there is no sign change, then all the poles of closed loop transfer function lies on the left half plane. And if there are sign change, then number of sign change is equal to the number of poles lies on the right half plane of a closed loop transfer function. Also, there are some limitation of RH criteria. If the system is nonlinear, then RH criteria is not applicable. And also, RH criteria not explaining the location of the poles in X plane. Actually, it is only define the criteria to explain whether the poles are lies on the right half plane or on the left half planes. And also it is deal with the coefficient of the characteristic equation if the coefficients of the characteristic equations are real. If the characteristic equation have the coefficient like sinusoids or exponentials are complex, then this criteria is not valid for those situations. And also it is unable to find the complete roots of the characteristic equation. Comparison of closed loop and open loop transfer function by using this block diagram where k equal to 1 and also unity feedback, then the open loop transfer function G1s is 240 by the poles at -1, -2, -3 and -4, and this is the again multiplication of these poles. If the open loop transfer function is 240 by s raised to power 4 plus 10 s raised to power 3 plus 35 s raised to power 2 plus 50 s plus 40, this is the open loop transfer function. And by using the closed loop transfer function, if we want to find the transfer function of this open loop transfer function, then it is by given this one. So open loop transfer function system is stable because all the poles are lies on the left half plane at -1, at -2, at -3 and -4. So what about the closed loop transfer function, whether the system is stable or not? So what is the criteria to find the stability? If we factorize this characteristic equation, then we are able to find the location of the poles. In our example, this is the fourth order system. If the order is higher, even more than 10 order, then we are unable to factorize the characteristic equation. So only RH criteria to find the stability of the system. G1s is the open loop transfer function, and from the open loop transfer function it is clearly indicate at all poles are lies at -1, -2, -3 and -4. So our four poles are lies on the left half plane in a complex plane. So system is stable in open loop transfer function. G of S is the closed loop transfer function. And how to define the stability of a closed loop transfer function? If we are able to factorize this, the characteristic equation, then we can define the stability easily. Alternate way is the RH criteria. How to apply the RH criteria? So first of all, we see how to fill the Routh table, in which first column representing the variables starting from the higher order and end with the lower order. In our case, s raised power is the higher order and s raised power 0 is the lower order. And first row is filled by using the alternate coefficients. For example, first coefficient is 1 and skipping the next coefficient, third coefficient is 35 and next skipping the 50 and the next one is the 264, and all skipped coefficient is filled in the next row. So this is the Routh table. How to complete the Routh table? In the Routh table, first two values are already completed, so third row can be completed by using the above two rows. So this is the definition to find the element of the row 1 and 10, 1 and 10. To find the first element using the adjacent element of the previous two rows 35 and 50 by solving this value. 1 multiply 50 is 50, 10 multiply 35 is 350, and scaled by this component. Third row is completely scaled by this value, which is 10. So first value is 30, and similarly to find the next value, minus first column is using similarly 1 and 10, and next column is the adjacent column of this element is 264 and 0, and by solving this relation answer is 264. So next all values will be 0 because adjacents above two rows are all 0. So this is the way to complete the third row. Similarly, we can find the rows of the fourth row by using the above adjacent two rows, which is s raised power 3 and s raised power 2. So first element of this fourth row is by using the 10 and 30, and next adjacent two elements are 50 and 264. After multiplying, 10 multiply with 264 is 2640, and 30 multiply with 50 minus 1500. So all values after calculation is minus 38. Similarly, next value is uh, 10 and 30 are the same column of this matrix, and adjacent values are the again 0. So in this case these are the two 0 values. So after manipulations we can find the values of 0, and similarly next all values will be 0. So last row can be filled by using the similar process. So in the adjacent two rows are the 30 have the values of 30 and minus 38, and the adjacent two values are the 264 and 0, and scaled by the just above value, which is minus 38. So 0 multiply 30 is 0, and minus and sign of minus with the minus formulation is 264 multiplied 38 is 10032. After scaling with minus 38, value is 64. So all next components of the rows will be 0. This slide only shows the result that in the previous case we are using the 10 and 50 value. Actually this whole row can be scaled with a 10, so this 0 can be cancelled out, so value remaining for the second row is 1 and 5. By using the similar process we can find the value of 30 to 64 and so on. So in the third row, in the last case we find the value was the 38. In this case we have the minus 3.8. So this is only the difference. To in the RH criteria, these values are not important. Only sign which are changing are important. For example, in our case, this first coefficient is positive and next coefficient is also positive and this coefficient is positive, and from 30 to 3.8 or minus 38 one sign is change, and similarly minus 3.8 to plus 264 another sign is change. There are two sign change. So result from the Routh table is clearly indicate in the next slide. Okay, this is the closed loop transfer function and this is the characteristic equation of order 4. Actually there are 4 poles. Without solving or factorizing by using the RH criteria, we were find in the last slide that there are two sign change. It means there are two poles on the left half plane and two sign are changed. This indicate that there are two poles on the right half plane. So out of four poles, two poles are lies on the right half plane. It means system is unstable. Uh, how many signs are changed in the first column? This indicates the number of poles which lies on the right half plane. Above results can be verified by using the MATLAB. So this is the open loop transfer function, and by using the unity feedback we find the closed loop transfer function. So this is the open loop transfer function, this is the closed loop transfer function, and by using the MATLAB we find that the in open loop transfer function R poles are lies on the negative half plane at -1, -2 and -3 and -4. So for closed loop transfer function, G representing the closed loop transfer function, so two poles are lies on the left half plane. For example, minus 5.39, for example minus 5.3 is, and plus 2.67 vertical value. So one pole is lies here and next pair pole is light here. So two poles are lies on the left half plane, and similarly minus 0.39, for example this is the and value is 2.67. So these two poles will lead the systems towards the instability. So system is unstable. This can be find the location of the poles. This lights is not clearly indicate, but this is the vertical axis and imaginary axis, this is the real axis. So this is the right half plane and this is the left half plane. So in open loop transfer function all the poles lies on the left half plane, and for closed loop transfer function this is the imaginary axis or vertical axis and this is the real axis, and clearly indicate in the MATLAB. This diagram shows that these two poles are on the left half plane and these two poles are on the right half plane. This leads toward the instability of the system. Okay, there is time domain comparison of open loop and closed loop transfer function. Interestingly, open loop transfer function is showing the stable behavior and closed loop transfer function showing the unstable behavior. But we can tune it toward the stability by using the different type of controllers. So another example to indicate the RH criteria. So G1s is the open loop transfer function and G of S the closed loop transfer function. How to find the closed loop transfer function? Relation is K G by 1 plus, if it is negative feedback then it is plus KGH. For unity feedback H is 1. So this is the closed loop transfer function, and this is the characteristic equation of the closed loop transfer function of third order. So how to complete the route table at already clear. So first vertical column representing the variables starting from the higher, in this example s raised to power 3 is the higher order, and then s raised to power 2, s raised to power 1 and up to s raised to power 0. First two rows is directly filled by using the characteristic equation. First row is the filled by using the alternate coefficient of the characteristic equation. Starting from the first coefficient, for example, s raised to power 3 have the coefficient is 1, so first element is 1, and then skipping the next 10, so after skipping next value is 31 and so on. Second row by filled by the skipped coefficients, in our case is 10 and 1030. How to complete the third row? By using the similar process. So first two elements of this column is 1 0, and to find the first element of the third row, next adjustments two values of the 31 and 1030. So multiply 1 multiply 1030 minus 10 times 31. So result will be minus 74. So minus 72 is the first element, and similarly next elements will be 0 because first coefficients are 1 and 0, and the next coefficient of this element are the 0 0. So this row component is 0, similarly next component is obviously 0. So to find the last row, first element can be found by using the 10 and 72 and 1030 and 0 value. So after manipulation, 10 multiplies 0, 10 multiplies 0, minus times minus is plus, 72 times 1030, and this minus sign is cancelled out by the scaled factor minus 72, and this value will be the plus, and this minus and this minus will be the plus. So this 72 cancel with 72, so answer will be 1030. So what are the result of from this the Routh table? So by observing the first column, first element have the positive sign, and next element have the also positive sign, third element have the minus sign, and fourth is the positive. So from positive to negative, one sign is changes. So negative 2 again positive is the second sign is also changes. There are number of sign changes equal to 2. It means out of 3 poles, there are 2 poles lies on the right half plane. So these are the results for the example. This is the closed loop transfer function, and 2 poles are lies on the right half plane, which tends the system toward the instability, and only one pole is on the left half plane. Our results can be verified by using the MATLAB. This is the real axis and this is the vertical or imaginary axis. This is the complex plane, RS plane. So 2 poles are lies on the right half plane and 1 pole lies on the left half plane. So system is unstable. Up to now we have 2 examples. It is clearly indicate that RH criteria is not explaining the location of the poles. Actually, if we are able to mathematically manipulate the characteristic equation, then we can find the location of the poles. But RH criteria is only indicate the how many poles are on the right half plane. So okay, these blue and red are representing the different inputs, impulse and the step inputs, and we will study the in detailed discussion in the next lectures what is the effect of different type of inputs. So here for the impulse as also with the step input, system tends toward the unstable. After completing the basic criteria of how to develop the Routh table, there are 2 special cases. First case is when the first element in any row is 0. How to handle this special case in RH criteria, we will see in next examples. And next special case is when the whole row is 0, and this is the more again important concept, that how to handle these special concepts. Let's see another example in which closed loop transfer function is given, and this is the characteristic equation, and this is the first special case. Let's see first of all how to complete the Routh table. First column as usually filled by the variables starting from the higher order, which is s raised to power 5, and end with the lowest order s raised to power 0. First 2 uh, rows are filled by using the coefficient of the characteristic equation, which are the real values. So first row is filled by the first coefficient, which is 1, and skipping the next element. Next one is the 3, and skipping the 6. Next is the 5, and then skipping the 3. So next row will be filled by using the skipped coefficients 2, 6 and 3. How to find the third row? Okay, this is the formula: 1, 2 and 3, 6 and scaled by 2. So 1 minus 1 multiply 6 minus 2 multiply 3 is 0. So this is the 0 in especially in first column. So next element is the, so how to find the element? 1, 2, 5, 3, find this determinant minus sign and scaled by 2. 3 minus 10 and minus minus will be positive, so 7 by 2. So first element is the 0. So this is the problem. How to handle this problem? So now this 0 is replaced by some small value epsilon. So by using the epsilon, we can find the next row, which is 6 epsilon minus 7 by epsilon, and the next value is 3, and similarly next one is a 0. By using this row element, we can find the next elements. First element is non-zero and next two are the 0, and similarly last element will be the 0 by using these two above rows. So this is the way to handle the 0 in the first column in a row. To find the result of this special case is we generate an additional table uh, in which we are using only first column, which is 1, 2 and epsilon, and similarly these are the first column components. Suppose we have epsilon is positive, then if this is positive, this is the positive, then this term will be the negative, because this is a small value which is less than 1. When multiplied by 6, it is always less than 7, so resultant will be the negative sign. And similarly, if we find the sign of this relation, it will be the positive, because epsilon square is here, so this is the epsilon, so this is uh, negative sign generating from the numerator and negative sign generating at the denominator will be cancelled out, and resultantly we can find the positive signs. And similarly third one is the 3 is a positive. Similarly we can find the again sign changes by using the epsilon as a negative. For example, in this row, if we consider this is negative, similarly we can find that next row will be positive, this row will be positive, and similarly this row will be also positive, and 3 is also positive. So resultantly there are two ways to explain the situation of first column. First one is positive and this is the negative, again positive and negative, sorry, it is positive. So if we're taking the epsilon positive, there are two sign changes in the first column, and similarly if we're taking the negative epsilon, again there are two sign changes in the first column. In both cases we find there are two sign changes in the first column. So there are 5 poles in this system. So this is the closed loop transfer function. There are 5 poles. Out of 5, 2 poles are lies on the right half plane. So this is the result for epsilon and how to handle the 0 in the first uh, element in the row. So as we see that closed loop transfer function have 5 poles. Out of 5, 2 poles are on the right hand side, right half plane, and 3 are on the left half of plane. By using the MATLAB we can verify our result that out of 5 poles, 3 are on the left half plane and 2 are on the right half plane. Okay, this is the vertical or imaginary axis, this is the real axis. These two are pair, we can find the roots, then this is representing the roots, this is the imaginary value, this is the real value. Similarly negative imaginary value and negative real value, and one pole is lies on the negative real axis. So 2 poles are on the right half plane, and due to these 2 poles systems tends toward the uh, instability. This is again the verification of the S-plane that systems is unstable. Next special case, a closed loop transfer function is given by this relation, and this is the characteristic equation, and this system have order 5. And similarly, first of all we complete the route table, and starting from the by filling the first column s to the power 5 from the higher order to the lower order s to the power 0. And next complete the rows. Actually there are 6 coefficients in this characteristic equation, starting from the first coefficient of higher order, which is 1, and skipping the 7, and next one is a 6, and then skipping the 42, next one is the 8. So first row will be 1, 6 and 8, and next row will be skipped coefficient, and those are 7, 42 and 56. We can continue even with the 7, 42 and 56, and maybe we can simplify by scaling the 7. So this 7 is scaled by 7 is 1, and similarly 42 scaled by 7 is 6, and 56 is scaled by 8. So next row is completing by using the route method, in which this element can be found by using the addition 1 1 6 0. Okay, 6 and 6 and scaled by 1, definitely it will be a 0. And similarly next element is 1 1 8 and 8, and also scaled by 1, again it is 0. And similarly this is 0 1 1 and 0 0 scaled by 1, so this is again 0. So this is the next special case, the whole row is 0. So this is a very important situation. How to handle this special situation, let's see. So if the whole row is 0, then consider the just adjacent above row, and consider the coefficient of this polynomial. In our case it is a 1 coefficient starting with the variable s to the power 4, and similarly next one will be 6 of s to the power 0, and next will be 8. So this is the auxiliary polynomial we consider by using the special criteria to handle this complicated situations. So we are skipping here alternate coefficients are, as already we skipping by filling the table by using the Routh criteria, and then taking the first derivative of this auxiliary polynomial, we have 4 s raised to the power 3 plus 12s, which is the just the which is representing the next row. This is s raised to the power 3, and this is also s raised to the power 3. So we can replace this 0 with this next coefficient, and similarly this 12 is replaced by this 0. So this is the criteria to handle this special case. So in this case we find the whole row which is already 0. Now by using this criteria, next element will be 4 and 12, and these element can be scaled by using by dividing the 4. So first element is 1 and 3. No, using these new values and complete the Routh table as previously explained. So in our case, we find there is first column have the positive sign in first element. Similarly, first this is also positive, and also this is a positive, and this is also positive, and this is also positive. So this is very interesting result. Out of 5 poles, there is no pole on the right half plane. It means this situation can be explained by using the special techniques to find the result. In our example, we have closed loop transfer function. Uh, this is the characteristic equation. There are 5 poles in the systems. So our poles are lies on the left half plane or on the imaginary axis. No pole is lies on the right half plane. This is very interesting result. This can be easily explained by using the MATLAB, and this is the result produced through the MATLAB. This is the real axis, and this is the vertical or imaginary axis. 4 poles in the form of pairs are lies on vertical axis, and only a single pole is lies on the left half plane. This is very interesting result. No pole is lying on the right half plane. System behavior is oscillatory for impulse input and also for the step inputs. Similarly, in our case, poles lies at different locations. If the case is different, if there are repeated poles, for example like this one, then this thing make the systems unstable. This shows the oscillatory behavior, marginally stable, and if the poles are repeated on the vertical axis, then this thing make the systems unstable. Stability in state space is also can be discussed through the RH criteria. In given systems, for example, in our case, this is the matrix A, this is matrix B, this is matrix C. We can find the eigenvalues of the system matrix by using these relations, and through this determinant of this relation, we can find the poles of the systems. So there is another method to find the stability of criteria without solving or without finding the pole is the RH criteria. Okay, let's see how to handle this situation. In our case, a system matrix A is given, and by using this relation Si minus A, I is the identity matrix, and this is the diagonal values of SSS, and by subtracting uh, the system matrix, we have this value, and finding the determinant of this matrix, ultimately we have s raised to power 3 minus 6 x raised to power 2 minus 7s plus minus 52. So how to find the stability by using this relation? Maybe someone can be solved by finding the roots of this equation and find the exact location of the poles. But alternate way to find the stability is the RH criteria. First of all, to fill the Routh table, there are 4 coefficients: 1, minus 6, minus 7, and minus 52. So as already explained, that the first row is consist of 1, minus 7, and 0, and second row have the element -6 and -52. In our case, -6 and -52 is scaled by 2, and finally we find -3 and -26. So by using the similar process as already explained, find the next component of the row, which is -1, and next these elements will be 0, and the last element is the multiple of this last element, which is -26. So in first column, first element have the positive sign, then it is negative, and the third row is also negative, and fourth row it is also negative. There is only one sign change. So what is mean by to find the location of the poles by using the Routh table? One sign changes mean only one pole is on the right half plane. Remaining two poles are on the left half plane. So results shows that one pole is on the right half plane and two poles are on the left half plane, and system is unstable. These are the MATLAB commands to find the transfer function, because system is represented in state space. So first of all, state space matrices A, B, C, D are given, and from the given matrix we can find the transfer function, and from the transfer function we can find the different type of behaviors, and also find the location of the poles, and also the pole zero map or pole zero location. By using the MATLAB command, we find the location of the poles. Okay, this is the real axis, and this is the vertical or imaginary axis. One pole is on the real axis and on the right half plane, and two poles in pair are on the left half plane. So this system is unstable. So if open loop transfer function is G1s, is k by s raised to power 3 plus 8s square plus 7s. So closed loop transfer function by using the relation as we already studied is Gs, which is equal to k by s raised to power 3 plus 18s square plus 77s plus k. How to study the stability of the system? By using this closed loop transfer function. Actually, RH criteria is applicable on the closed loop transfer function. So first of all, we develop the Routh table. How to derive it? We have a closed loop transfer function, and denominator term, a characteristic equation is given by. So by putting the coefficient of this characteristic equation of closed loop transfer function into a first row and the second row of the Routh table, which is 1 and 7, and this coefficient of higher order is 1, and the third term with the coefficient of 77. Similarly, remaining coefficient is filled in the second row, 18 and k, and complete that table as this is already. So first column defines the stability by using the RH criteria. So except k, remaining values are the constant 1, 18, 1, 3, 8, 6. So how to define the stability by using the value of k? If k is because k is already, we defined that k is positive, if the range of k is in between of 0 and 1386. So for example, it is a 12. If we're taking the 12, then this value will be also 12, and 1386 minus 12 is a positive term, and similarly last term also positive. So in this case there is no sign change. It means all the three poles are on the left half plane. So if we're taking the value greater than the 1386, then this term will be negative, and this term will be positive. It means there are two sign change from 18 to this negative value, and similarly from negative to again this is the positive value. So there are two sign change, it means there are two poles on the right half plane. And what will be happen if k is equal to 1386? So this is the special case as we discussed in the previous portion of the lecture, that if k is equal to 1386, then this term is equal to 0. So now you can easily solve this special situation. If first term of the Routh table is 0, how to handle it? Let's see. So we already discussed how to handle this situation by taking the above adjacent auxiliary polynomial, which is 18s square plus 1386, and taking the first derivative. So the coefficient of this polynomial is filled in the next row, which is 36. Now replace 0 with 36 and next is a 0. So all the terms are positive. It means there is no pole on the right half plane. So closed loop transfer function is also is given in this slide, and result can be easily explained by using the different values of k. By keeping in mind the previous Routh table, if the range of k is 0 to 1386, then all the poles are on the left half plane. There is no pole on the right half plane. If we take the value greater than the 1386, then the two poles on the right half plane. And if this value of k is equal to 1386, then also again there is no pole on the right half plane. So what will be the situation? So it will be can be seen easily through the simulation. I will assume k for the first case equal to 12, and the for second case is equal to 15, and for the third case is equal to 1386. So what will be happen if the k is less than 1386? It is equal to, in our case, suppose it is equal to 1200, then all the poles are lie on the left half plane. Okay, by using the value of k is equal to 1200, system behavior is stable for both inputs, for impulse and as well as for the step inputs. The next case, if we take k is equal to 1500, which is greater than 1386, the critical situation, so both two poles are on the right half plane and in the form of pairs. And if we further increase the values of k, then these poles move from this position towards the right half side, and due to these situations systems tends towards the more instability. These simulations shows for values of k equal to 1500, systems is unstable. If we take k is equal to 1386, then the system behavior is oscillatory and the two poles are on the vertical axis. This example is very important, especially if we want to design the controller of value, any value of k, and the RH criteria is applicable on these type of systems if the closed loop transfer function is given. And by using the RH criteria, we can easily design the value of k for these type of systems. If we choose value of k is equal to 1386, then the system is marginally stable and the oscillatory behavior shows for the impulse input as well as for the step inputs. So this is the very interesting case, and it will be helpful to understand the Routh-Hurwitz criteria if we changing the values of k, for example, here are the repeated pair poles in pairs for different value, and if we change the values of k, for example 1385 poles at lies on the vertical axis and oscillatory behavior showing in these graphs, and if we increase the values of k, poles, closed loop poles of the systems are showing on the right hand sides. So this is a very interesting case, and this case also helpful to understand the Routh-Hurwitz criteria. So in this lecture we cover the almost complete portion of RH stability criteria. Routh-Hurwitz, how to develop the Routh table, and what are the limitation of RH. Sometime RH criteria is not applicable because if the coefficients of the polynomial are not real number, then it is not applicable. And also we discuss the some two special cases when the first term of the first column is 0, and if the and second case when the whole row is equal to 0. And also we discuss the how to apply the RH criteria in state space, and also in the last portion we study that how to design the values of the controller by using the stability criteria. So thank you so much.